Hello everyone, welcome back to this course on discrete mathematics, and now we are going to look at series of lectures based on graph theory. We have already seen graph theory part 1 where we discussed about the basics of graph theory, and today we are going to look at some of the properties of graph theory in this lecture. Let's directly go on to this graph. For example, consider this two graphs. The question is, are they same? Well, you can see whether these vertices and edges are they preserved. Well, yes, these two graphs are same, but just a different drawing. How about this two? Well, yes, they are the same, but it has a different label. Instead of 257 you have Albert, instead of 122 you have Grant. Yes, the same graph but different labels. So the question here about this connectedness, we have this similar connections of two graphs that have different representation is called a graph isomorphism. So all that matters is the connections in the way they are connected. Graphs with same connections are isomorphic. So informally, two graphs of isomorphic, if they are the same after renaming or relabeling. Isomorphic has applications like checking fingerprints, testing molecules, and etc. So there are a lot of applications where we can go for this isomorphic. So again, another question here, are these two graphs isomorphic? It looks quite different, but let's examine one by one. One way to do is that try to see whether all edges and all vertices are preserved as it is preserved in the original graph. Say for example here this node, consider the node dog is equivalent to the node beef, the node cat is equivalent to the node tuna, and the dog and cat are connected, beef and tuna are connected. Then comes the pig is connected to corn, and the cow is connected to hay. Then again you can see how other connections are going along the way. How cow is connected to both dog and cat, again the corn is connected to both beef and tuna. Likewise, hay is connected to both beef and tuna. So that's nothing but the similar approach how the cow is connected. And corn is connected to beef and tuna, which also refers to the pig is connected to dog and cat. Well, a bijection, that is, we are going to deal with this phenomena, these notions of bijections. The question is, edges preserved, or is all edges are preserved? If there is an edge in the original graph, there is an edge after mapping, there should be. If it is not preserved, it cannot be an isomorphic. If it does, for example, cat and dog, beef and tuna, yes, each and every edge you have to check whether they are preserved or not. If the edges are preserved, then we can say these are isomorphic. Non-edge preserved, if no edge in the original graph, there is no edge after mapping. For example, cow and pig are not connected, there is no edge in the original graph, so therefore there is no edge from hay and corn. That's simple. Right. So G1 isomorphic to G2 means there is an edge preserving vertex matching. Let's consider this. V1 implies V2, where UV in E1 if and only if f of u implies f of v in E2. So UV is an edge in G1, and the f of u and f of v is the edges in G2. Again, there are a few questions here for us to determine whether a graph is isomorphic, and it also expresses some of the properties of isomorphism. If G1 and G2 is isomorphic, do they have the same number of vertices? What do you think? Well, yes, they should have same number of vertices, right? And if G1 and G2 are isomorphic, do they have the same number of edges? Yes, they have same number of edges, because we talk about edge preservation. And if G1 and G2 are isomorphic, do they have the same degree sequence? Yes, they have same degree sequence, because the number of edges connected to a particular vertex is same in both original as well as in the new graph. If G1 and G2 have the same degree sequence, are they isomorphic? This is the similar question that's been turned around. No, not necessarily. If G1 and G2 has same degree sequence, it is not necessarily an isomorphic graph. So checking whether a graph is isomorphic, the question is how to show two graphs are isomorphic. Well, now you know some points, like there should be the equal number of edges, equal number of vertices. Thereafter you also talk about the degree sequence should be the same. And what else? Let's consider a few points. Find a mapping and show that it is edge preserving. Try to find a map for each and every edge equivalent in both graphs. How do you show a graph is non-isomorphic? Find some isomorphic preserving properties like edge preserving, which is satisfied in one graph but not in another. That's a simple way of disproving. Again, the question is given to us with these two graphs. So they have the degree sequence of 2, and all degrees are 3 in this one. Therefore, these two are not isomorphic graphs. Again, now let's talk about some more notions of graph theory. We call path. Path is a sequence of adjacent vertices. Say for example, here the sequence of adjacents, as you can see, starts from black, goes to red, then to blue, then to yellow, red, and pink. So that is the path that has been defined in this example. A simple path is all vertices should be different. Say for example, yellow, blue, red, pink, green, and black. So that's a simple path which has distinct vertices, whereas in the previous one we saw that the red is repeated twice. So that's just a path, but a simple path should have a different vertices. In other words, it just passes through it only once. Connectedness. Let's talk about the connectedness of a graph. A vertex V, W are connected if and only if there is a path starting at V and ending at W. So let's discuss about this connections. Yes, a graph is connected if and only if every pair of vertices are connected. Every pair of vertices are connected. That's one of the property. Every graph consists of separate connected pieces called connected component. So we will see this here. As you can see, 3 connected components are there. The first one is has 13, 10, 12, 4, 26, 8, 16, 66. These are all connected. The second one is just vertex is there. The third one is E17, E25. So here the graph is connected if and only if it has only one connected component. Then comes the cycle. A cycle is a path that begins and ends with the same vertex, just like a circuit or a cycle. For example, here we have this graph, and you have this path that starts with V, goes to B, then to W, and again there is a loop in W, then comes back to W, goes to A, and comes back to V. Because it forms a cycle in this, coming back to the same vertex again, we call it as a cycle. We can also have A, V, B, W, W, A, or you can have B, W, W, A, V, B. Yes, these are all forms a cycle. Simple cycle. A simple cycle is a cycle that does not cross itself. So in the previous one we saw that this cycle crosses W every time when we make a cycle. It's something similar to the path and simple path. A simple cycle is a cycle that does not cross itself. So here you can consider W, V, W is a simple cycle, as well as V, W, V is also a simple cycle. In a simple cycle, every vertex of degree exactly 2, because it is just passing by. Shortest path. A path between U and V is as a shortest path if among UV path it uses minimum number of edges. So consider there are 2 nodes UV, and you want to find shortest path between these 2 nodes. The shortest path would be that minimum number of edges used to reach from U to V. Is shortest path between 2 vertices always simple? As you can see here, if you are considering U and V, so if you just remove this cycle, it would be more easier. So idea, remove the cycle will make the path shorter, or else you just go to C point and then just go to a cycle. After that you go to the point V. Yes. Coming to Euler's graph. Euler's theorem, a graph has an Euler path if and only if it is connected and has at most 2 vertices with an odd number of edges. So if you recall Euler's theorem, we talked about Euler's path at the beginning of previous lectures, where I introduced about the graph theory, and we talked about this odd degree vertices. Can a graph has only one odd degree vertex? As the Euler's theorem states this, a connected graph has an Euler path or Eulerian path if and only if it has 0 or 2 vertices with odd degree. So that is one thing, but we are not going to consider the whole induction process, but we will see to some degree how a connected graph has an Eulerian cycle if and only if every vertex is of even degree. Let us see, we have this Eulerian cycle as shown here. So to begin with, you can see there are different vertices, 8 vertices at this location, and let us name them. So note that edge can be partitioned with 5 simple cycles. According to this problem, we can in fact separate, and vertex of same color represents the same vertex. Say for example, you have green, they are the same vertex when they are connected, and then you have yellow, you have blue, you have orange, you have red, you have purple, you have other light greens. All these are the same vertex. Let us get started with this Eulerian cycle process. To begin with, the idea is that we can construct an Eulerian cycle by adding cycle one by one. Let us try to traverse this whole system with cycle 1. As you begin, say for example, you are starting from this process of 1 and you are entering 2. So that is like then you are trying to traverse to the second cycle. So say for example, you started from red and going to the blue in the first cycle, and after that you are going back to this red one, and from red you are connected to the second cycle where you are going to the third part, and from third it is going to the fourth one, and from 4 you are going to 5, and from 5 you are going to 6. So this means that at the point of 6 you are reaching the cycle for the cycle 2, but at 5 in fact you can go to cycle 3. You can go into the third cycle if you detour the third cycle before finishing the second cycle, just like 6. From the green you are entering into the third cycle, so you are going into the 6 and 7, 8. If you go back to 9 you will finish the cycle, but we can skip this as well. But if you go back to 10 you are going to the cycle 1 in fact, but after 7 in fact you can go into the next cycle with the 8, 9, 10, 11, you can come back to this whole system. Instead, in fact, you can also go back to this last cycle, that is fifth cycle. We can insert the fifth cycle in the intersection. So as you go backwards, you are going to delete these unwanted path. Is with the 16 paths you are coming back to the first one. So if you recall what have just happened, you can, considering this whole system, you can see how things would work out. Say for example, if you started from cycle 1, you had 2 paths, and then you are entering cycle 2 for the path 3 and 4 and 5, then you are going to the path 6, 7 in cycle 3, then you are going to path 8 in cycle 4, then for path 9 and 10 is cycle 5. Then on your way back you are entering with 11, 12, 13 for in cycle 4, 14, 15 in cycle 3 and 16 in cycle 4. In fact, when you say 16, that's the path that meets us from green to blue, and that blue has a common point with cycle 1. Since blue has common point with cycle 1, it all merges together for us to form this whole system. As this is in fact a connected graph, and you can see how this Eulerian path has been developed, and we have considered this whole system of vertices as we go from one cycle to another cycle. By the definition of cycle and path, right now you are familiar with how this Eulerian cycle has been established. Yes, this is a simple example that we have just seen. So in general, if we have a partial Eulerian cycle C star and it intersect with a cycle C on a vertex V, then we can extend the Eulerian cycle to include C. So say for example, in this figure you would notice that we have a partial Eulerian cycle of C star is an Eulerian cycle, and it intersect with the cycle C. Did you notice that is the cycle C is being intersected on a vertex V? So that is the part where it intersects. Then we can extend this Eulerian cycle C star to include C. Or since we are talking about this Eulerian path, and in fact we also talked about this shortest path. Do you recall it? We will deal with this in a short time when we talk about the shortest path in our next lecture. We call something like a minimum spanning tree, and in which you are trying to find the minimum cost, as well as we can recall other ideas of shortest path. So since we talk about cycles and path, I like to just briefly talk about this so-called shortest path. Well, you might have heard about the traveling salesman problem, or in other words it's called TSP, the famously called TSP, traveling salesman problem. So this is a simple problem in which a traveling salesman, he goes to different city and he covers an entire territory that is given to him. But the question is he taking the shortest path from one place to another place, and is he taking the cost effective route as well as he goes along the whole path? So the constraint is about the cost and the distance. So we are looking at the shortest path and the minimum cost. With this they can determine a feasible solution. And again, this traveling salesman problem is one of the applications of graph theory. Apart from that, for even placing the circuits in an IC, the so-called VLSI IC chips, very large scale integrated circuits, we can also define the entire system, entire network by means of a graph based solution. Is that all? We talked about how graph theories are used in smart cities as well. Well, apart from the smart cities, if you consider even all these roads in a city, or all the highways in a city, or you can also consider the entire network of vehicles in the city. Yes, these can also be modeled using the entire system of graph theory. Yes, that graph theory has a wide range of applications. Since we have already talked about this Eulerian path, Eulerian cycles, and in the next part of this lecture also we will consider a few more sections of it. So let us briefly see this claim of the proof. If the edge of a connected graph can be partitioned into simple cycles, then we can construct an Eulerian cycle. So if the edge of a connected graph, edge is the line, the edge of the connected graph can be partitioned into simple cycles, then we can construct an Eulerian cycle. So the Eulerian theorem is that a connected graph has an Eulerian cycle if and only if every vertex is of even degree. You remember what is a degree, right? So let's see the claim 2 here. If every vertex is of even degree, then the edge can be partitioned into simple cycle. Did you see the claim 1 and claim 2? And in between you have this Eulerian theorem. Yes, initially we are told that if edges of connected graph can be partitioned into simple cycles, we are going to have Eulerian cycle. But for Eulerian cycle, it says a connected graph has an Eulerian cycle if and only if the vertex is of even degree. But if the vertex, every vertex is of even degree, then the edge can be partitioned into simple cycle. That's the claim 2. Yes, today we have seen a very simple outline of various properties of graph theory, and there are still more properties remains. Especially I will just highlight you some of the applications of graph theory, generally speaking about the spanning tree. In fact, we talked about graph, and in the next lecture we will talk about the so-called trees. Until I catch you in the next lecture, have a good time and goodbye.